Okay, so yesterday we started with GCD, we saw the Euclidean algorithm, and we also saw the uh, extended Euclidean algorithm. So in today's lecture, I'll start with modular arithmetic, and then eventually we'll see where we can use the extended Euclidean algorithm in a particular operation of modular arithmetic. Okay, so let's start. Let's start with something called as congruences. So two numbers A and B are congruent congruent mod, the full form is actually modulo. In short, it is written as mod m, and it is written as A. Instead of equal to, we have this sign for congruence, three lines. Okay, so A is congruent to B mod m if, so this is the definition, you can say A is congruent to B mod m if A minus B is a multiple of m. Okay, the integer m is also an integer. Okay? M is also an integer, and for this particular class or this particular course, we'll consider only positive m, and m is called as the modulus. M is called as the modulus. Okay, only 31 people have joined. Any issues with? Is my audio all right? So m is the modulus. Now just see these examples. Okay, so these are all valid examples that I will give you, and so that after seeing these examples, you'll become familiar with the operation basically. Okay, so 7 is congruent to 1 mod 6. 14 is congruent to 0. I'll just write these things. Okay. In all these cases, you can see that the LHS minus the number on RHS is a multiple of the modulus that you can mentally verify. You know. Okay, so I'll wait for a minute. Just go through these examples and make sure you get a feel of this operation, basically. All right, so let's proceed. If you have any questions, you can ask in between. So, okay, another thing that we can say.
So can you speak a bit louder? I can't hear you.
Okay, okay, wait a minute. Okay, is it better now? Is it better?
Yes.
No, sir, a bit. If you can increase a bit more.
This is the maximum I can go. Is it okay?
Okay, sir. Okay, yes, sir.
Okay, so now we can say one more example. So any integer n is even if and only if that integer is congruent to 0 mod 2, and integer n is odd if and only if n is congruent to 1 mod 2. Okay, so by definition we are saying that a is congruent to b mod m, means a minus b is a multiple of m. Okay, so we can write this as, okay, can write this as a minus b is a multiple of m. So multiple means something multiplied by m. So let that integer be k. Okay, so a minus b equal to km if a is congruent to b mod m. Fine. Now, what is the another interpretation, or we can say, what does it stand for? What is another way we can look at it is that, okay, so we can say that a and b, okay, and write the statement as a and b leave the same remainder, leave the same remainder when divided by m. A and b leave the same remainder when divided by m. Okay, now there is a slight distinction now. Okay, there is a new terminology, it might be new for you. Now there is something called as a residue. Okay, and so, okay, let Okay, let's just consider. Okay, so up to this point, is it clear? Any questions up to this point? Anyone has?
So the last thing only, I didn't get that. A minus B is equals to Km, and after that, A, if A and B leave same remainder, that one.
Okay, okay. Well, A minus B equal to Km is by definition. Okay, so the definition of this congruence, definition of congruence is that A is congruent to B mod M if A minus B is a multiple of M. When we say is a multiple of M, then K is the factor that we are talking of. Okay, so this is the mathematical way of saying the sentence that A minus B is a multiple of M. This is this. And the second part is A and B leave the same remainder when divided by M. Now this part I'm going to explain further now. I'll explain further. So, okay, let's leave the terminology B for a while. Instead of B, what I'll use a different letter for ease of understanding. So okay, suppose you have a number A and you have to divide it by another number M, and these are the numbers with you. A and M are the numbers with you. They're integers, in fact, and M is positive. Then we can say that A is congruent to R mod M. Okay, A is congruent to R mod M can be said as M divides M divides A minus R. M divides A minus R. Okay, so this you can, in terms of division, if you want to express it in terms of a division operation, or in terms of dividend, divisor, quotient, and remainder, if you want to write it that way, you can write it as A is equal to the quotient. In this case, is quotient we'll call as Q. Is a Q into M plus R. A is equal to Q into M plus R. Okay, so you divide A by M, and the remainder that you get is R. But if you subtract the remainder from A, right, you will get A minus R, and then M can perfectly divide A minus R. A minus R is Q times M. Okay, in terms of AB, if I write the same thing in terms of AB, it will be A is equal to Km plus B. But in terms of, Q is for quotient, R is for remainder, I think this will be better to understand in this way. Are you getting this? Did you get this point? Yes. Okay. So which equation? Which equation to repeat? Which equation exactly? A is equal to Qm plus R. Okay. Okay. Fine. I'll repeat it once again. So A is congruent to R mod M is just an equation. Okay. Just consider this as an equation. A is congruent to R mod M. Okay. Now by definition of congruence, you can say that A minus R is a multiple of M. A minus R is a multiple of M. Okay. This is clear. You agree with this part? By definition, yes, A minus R is a multiple of M. The other way to, you can move the sentence around, and you can say that m divides a minus r, right? M divides a minus r. Okay, now interpret this as, okay, we are interpreting this as a is a number which you are dividing by m. A is a number which you are dividing by m, and after dividing by m you get the quotient as q and remainder as r. So therefore this is the equation that a is equal to qm plus r. Okay, and then it fits our description, or it fits our definition perfectly, because if you take the remainder out from a, that is if you perform a minus r, then a minus r is a multiple of m, that is q into m, or in other words m divides a minus r. Is it clear now? Okay, so in this case now there is only one issue here, not issue, what we can say it is a technicality, is that the remainder, that is r, okay, remainder should be, what will be the range for the remainder? Remainder can be 0, or it can be at the most less than, strictly less than m. Okay, so if I use less than equal to, it will be m minus 1. So the remainder will be between 0 to m minus 1. Okay, so what happens is, okay, so I'll write both the things here. Okay, if I started with a is congruent to b mod m. Yes, okay, a is congruent to b mod m, and on other side I'm writing a is congruent to r mod m. Okay, so if this RHS number, okay, if this is within 0 to m minus 1, if this is within 0 to m minus 1, then it is called as, in number theory the terminology is, it is the least positive residue. Least positive residue, but in common terminology we call it as the remainder. Okay, it is the least positive residue. We can also call it as the remainder if it lies between 0 and m minus 1. Okay, but if it does not lie between 0 and m minus 1, then we can say that what I wrote before, that a and b, you know, just what I wrote before here. Okay, a and b leave the same remainder when divided by m. Okay, any questions, or shall we proceed? Shall we proceed, or any questions? How a and b will leave the same remainder? Uh, what do you mean by that question? Can you give any counter example in any of these cases? And our remainder is a, so
Hello.
number between 0 and
Hello.
n. Yes, yes. Who is speaking?
Hello. Sir, you said that A and B will leave the same remainder.
Yes.
If the if it is not between 0 to m minus 1.
If b is not between 0 to m minus 1, or like,
Yeah.
that is
Yes.
okay, but any counter, why do you doubt this? Any counter example you have? Why is it a question?
No, I didn't get that.
Hmm. Well, the reason is because, okay, I don't want to confuse you any further with this, but the reason is because A minus B equal to Km. You can also write it as A is equal to B plus Km. Okay, A is equal to B plus Km. Aditya, agree?
Yes, sir. Yes,
Yes.
sir.
So because you are adding a multiple of M to B, the remainder will not change, right?
Yes.
Get the point? Okay. Anyone else has any questions, anything, or shall we proceed? Shall we proceed? I'm waiting for your comment. Reply in the comment if we can proceed or not. Yes? Okay. So now there are some. Okay, now which part to repeat? The last line. A is congruent to R mod M. Okay, I'll.
Sir, if it is
Which space?
if remainder lies between 0 and m minus 1, then it is called least positive residue. And if it is not,
Yes.
then what is it called?
It is called nothing. It is just, A and B are congruent. We just say that A and B are congruent to each other with with respect to mod M. Okay. If B is
Sir,
not.
if
Yes, yes. Speak. Speak.
this condition is not satisfied, then what is it called?
No, see. A and B are just any two numbers that we have. Okay.
Yes.
Right. So in general, we say that A is congruent to B mod M if A minus B is a multiple of M. Okay. In other words, we can say that A minus like A and B leave the same remainder when divided by M. Okay, so there is no separate name for A or B. We can say that A and B are
Okay, sir.
congruent. A and B are congruent. Only if where B is written, if we have something which is within 0 to M minus 1, then we can say that it is the remainder when A is divided by M. Okay, getting it?
Yes, sir.
Okay. So one more example I'll take, and this is.
Sir, A and R also are congruent to each other, right?
Yes, they are congruent to each other. That terminology still can be used. They are congruent to each other. Yes. Okay. So minus 3 is congruent to dash mod n. Fill this dash. And I want the least positive residue or remainder. I want the least positive residue. What will be there in this dash? Reply in the chat quickly. Zero. Minus 3 divided by n you are performing. No. What is the closest multiple of A? No, there is no restriction on A. There is no restriction on A. I only said when starting the lecture, I only said that M should be positive. Yes, 6 is correct. M should be positive. So your remainder will be positive. Remainder will be a positive number between 0 and M minus 1. Okay, A, B can be anything. That's why I asked you to go through these examples. These examples have everything. Okay, sometimes A is negative, sometimes B is negative. You know, everything is there in this example almost. So 6 is correct. The nearest multiple is -9, and difference between -3 and -9 is 6. So 6 is correct. Okay, so the next thing is there are some properties. There are some properties. Okay, so A is congruent to A mod M, obviously. Okay, now if A is congruent to B mod M, then B is also congruent to A mod M. B is also congruent to A mod M. Because A minus B is a multiple of M, and B minus A will also be a multiple of M. In previous example, can't we assume Q is 1 by 3? No, Q is an integer. We are only dealing with integers here. Okay. So A is congruent to B mod M, then B is also congruent to A mod M. If A is congruent to B mod M and B is congruent to C mod M, so you can say that A minus B is equal to Km, let's say, and B minus C is equal to Lm. Okay. So if you go by this analogy, A is congruent to C mod M. If you use this logic, so A minus B is a multiple of M, B minus C is a multiple of M. Therefore, A minus C is a multiple of M as well. Okay. Then next thing is, okay, this is interesting.
Excuse me, sir.
Yes.
Sir, after you finish these properties, can you re-explain that example above -3, 1?
Okay. Okay. So if A is congruent to B mod M and C is congruent to D mod M, then you can combine these as A plus C is congruent to B plus D mod M. Okay. A minus C is congruent to B minus D mod M, and AC is congruent to BD mod M. Now I'll come to that remainder part again, but this last property, it is useful in something. Okay, like we can extend this property. It is a very useful property. All these properties you can easily prove. You know, you can mentally also, like A minus B is Km and C minus D is Lm. Okay, because these are multiples of M and these follow naturally. So if we say A plus C, you are adding these or subtracting these or multiplying these. So these follow naturally. Okay. Now this last property which is there, AC is equal to BD mod M. Now consider you want to find a remainder when a large number is to be divided by m. Okay, so as a small example, let's say, now you can do this easily, but still, first we'll start with a smaller example. So let's say you want to find the remainder when 49 is divided by, 49 is divided by 6. You want to find the remainder. Now you already know that 7, when you divide it by 6, the remainder is 1. Now you can use the last property as, okay, so this will become your A, B, C, D. So your AC, that is 49, is congruent to BD, which is 1 into 1 mod 6. And therefore you can say that, uh, 49 is congruent to 1 mod 6, or you can say that when 49 is divided by 6, the remainder is 1. Now this is the simple case, but let's say you are given some large number. Let's say you want to find the remainder when 7 raised to 200 is divided by 6. So even in that case, you can repeatedly apply these rules, okay, and you can find the remainder. Okay, so for 7 square, it is the same thing. For 7 raised to 4, it will be again 1, and so on. Yes, so my point here is, even for a larger number, you can use this property and find this. I'll give you another example of this because this is important. Okay, this is something called as what we are, okay, the terminology or the concept that is here, or the concept that we are reaching, is called as modular exponentiation, and it is very useful in cryptography. Modular exponentiation. Okay, so you have some number which is raised to a huge exponent, and then you have to find its mod, the remainder, basically. So let's take another example. 3 raised to 5 mod 7. By this, what I mean is, I want to find the remainder. Okay, I want to find the remainder when 3 raised to 5 is divided by 7. Okay, it is in literature or anywhere, it is also commonly known as find 3 raised to 5 modulo, or okay, find the congruence of 3 raised to 5 modulo 7. Directly you can write it in this way as well. Okay. Okay. Assuming that you will not get any more confused by this, like, because by this rule, okay, as we said that A is congruent to B mod M, then B is congruent to A mod M. So we can say that, whatever the answer will find, the 3 raised to 5 is congruent to R mod M. We can also turn it around and we can say that R is congruent to 3 raised to 5 mod 7. 3 raised to 5 is congruent to R mod 7. R is congruent to 3 raised to 5 mod 7 by definition of the mod operation, the congruence operation. Okay. So how will you go ahead for this? So we can say 3 is congruent to 3 mod 7. Then we'll find for square. 3 square is congruent to 9 mod 7 and 9 mod 7. Okay, 9 mod 7. This is just literal, 3 square is 9. But if you want to write it in terms of least positive residue, you can actually perform the division and you can say that it is congruent to 2 mod 7, because 9 when divided by 7 leaves a remainder of 2. So you can say that 3 square is congruent to 2 mod 7. Then 3 raised to 4 is congruent to, now 3 raised to 4 is 3 square into 3 square. Now on this side you have 2 into 2 mod 7. So therefore it is congruent to 4 mod 7. Okay. And finally we want 3 raised to 5. So 3 raised to 5 is 3 into 3 raised to 4. It is congruent to, for 3, the RHS is 3 itself. Congruence or RHS you can say is 3 itself. For 3 raised to 4, it is 4 mod 7, which is 12 mod 7. Now we can leave it at this. It is congruent to 12 mod 7, but we want to find the least positive residue, or we want to find the remainder actually. So 12 mod 7, the actual remainder is 5. So we can say that is congruent to 5 mod 7. Okay, so at no point, so still, 3 raised to 5 is also possible to be calculated in your calculator or in your head, whatever. 3 raised to 5 is 243, and 243 you can actually divide by 7 and you can find the remainder. But in all these 4 steps, we never divided such a large number by 7. We did not divide 243 directly by 7. Okay, we tried to divide 3 by 7, which is, implicit. 9 divided by 7, we did, remainder was 2. Then we divided 4 by 7. You see the numbers that we are perform the division with are very small. 12 divided by 7 and so on. Okay, and it is true for even larger powers. So okay, after this I will return to your that earlier doubt that you had raised. But this can also be used in case of, let's say you have any arbitrary power 3 raised to 385, for example. Now what power, like, okay, I'll give you a hint, or I'll give you the steps. So if you can convert 385 into binary. Okay, so do you know how to convert decimal numbers into binary? Yes or no? You know, right? So 385 in binary, just try to convert it in a minute. Can you convert it right now? Or I'll write the answer, you just verify. Multiply by 2 and use the remainder. Well, you can, no, it's like, 385 is 2 into 192. You mean to say divide by 2, right? 2 into 192 plus 1. Okay, then 192 is 2 into 96 plus 0, and so on you will perform. So the number you will get is 1 1 0 0 0 0 0 0 1. Okay, binary. So what does this binary representation indicate? That 385 is the sum of, you can say, 256 and 128 and 1. Okay, so we are expressing the exponent, that is 385, as the sum of powers of 2. And now what we'll have to do is, we know the modulus for 3. We know the modulus for 3 square. From 3 square we found for 3 raised to 4. 3 raised to 8 can be found from 3 raised to 4. 3 raised to 16 can be found from 3 raised to 8. Okay, I'm not doing this. Maybe I'll add it as a tutorial question. Okay, with a different modulus maybe. Do you get the point? What I'm trying to say? When you have the necessary powers of 2, instead of This is a faster way of performing the exponentiation as well as modular exponentiation. Okay, so from 3 raised to 16 you can calculate 3 raised to 32. From 3 raised to 32 you can calculate 3 raised to 64. So powers of 2 will not have the same remainders. No. Powers of 2. See, 3 square had the remainder 2 when divided by 7. 3 raised to 4 had the remainder of 4 when divided by 7. Actually, I can, okay, I'll just write this down here itself, okay? This will be very interesting for you and it is something useful as well. What happened? Okay. Okay. So 3 raised to 1 is, I'm just writing the remainders now, okay? 3 raised to 1, remainder is 3. 3 raised to 2, as we found, 9 mod 7, remainder is 2. 3 raised to 4 is 2 into 2. The optimization that we are performing here is, we are not actually calculating 81 divided by 7. We are doing, 2 into 2 divided by 7. 4 divided by 7 we are performing. Are you getting the point? Then for 3 raised to 8, whatever 81 square is, I think 81 square is something like 6561. I don't know, you can verify. 6561. So we are not dividing 6561 by 7. What we are doing is, we know that for 81 the remainder is 4. So for 6561 the remainder will be the remainder that we get when we perform 4 into 4 mod 7, which is 16 mod 7, which is 2. You get the point here? Okay. Okay, so we'll keep some examples in tutorial. So this is called as modular exponentiation. Also, you can calculate for the odd powers. It is not very difficult for odd powers as well. 3 cube is also not very difficult using 1 and 2. Okay, once you find the powers of 2, then the remaining powers in between, they are not very difficult to calculate as well. Using the powers of 2, you can do that. So what was the point? So this was about modular exponentiation. Okay, now coming to your question. Okay, where was that? Why we converted to 385 in binary? Okay, because we wanted to find, or we wanted to find out which powers of 2, like 380, any number can be expressed as sum of the powers of 2. Any number can be expressed as sum of powers of 2. Okay, and it becomes faster to calculate exponentiation if we use that technique. Okay, that's why we saw which powers of 2. Okay, so I left it here. Okay, so from 3 raised to 64 we can find 3 raised to 128. From 3 raised to 128 we can find 3 raised to 256. Okay, and then whatever the remainder we'll get for 3 raised to 256. And okay, so 385 is 256 plus 128 plus 1, right? I'll write it down again here because it becomes messy. 385 is 256 plus 128 plus 1, which means when I want to calculate 3 raised to 385, it will become 3 into, 3 raised to 256 into 3 raised to 128 into 3. Right? You get this statement? Okay. So that's why we found the powers of 2. We converted it into binary to find which powers of 2 are there, and because we want to calculate in this manner, typically. And it is easier that way. So yes. Your doubt was how did we get this, right? Okay. So when I'm saying remainder, okay, so let's say where are the multiples of 9? 9, 0, minus 9. Okay, and minus 3 is, let's say, somewhere here. Now if I use, so what should happen is my remainder should be positive. Okay, so here my A is minus 3. Okay, if I use, okay, I'll ask you. Okay, if I use 0 as my multiple of 9, what will be the remainder? Zero will not be the remainder. Not 9, not 3. Okay, wait. What is the remainder? What is the concept of the remainder? Okay. Where did I had written that somewhere, right? A is equal to QM plus R. Okay. So here my A is minus 3. A is minus 3. Quotient I don't know. Okay. This is this. And remainder I don't know. These are the two blanks that I want to fill. Now LHS will become equal to RHS. Now if I use the, okay, where should I write this? Okay. If I use, yes, someone is speaking something. Okay, if I use quotient at 0, if I write 0 over here, what will be the remainder? Now reply. Quickly. Yes, remainder will be minus 3. If the quotient I use is 0, remainder will be minus 3. But which is not what we want. We want a remainder between 0 and m minus 1. Okay. So what is the other option? What will happen if you use q equal to 1 over here? Will it work? If you use q equal to 1, it will be, what will be r? Just tell me. Come on. Q 1 plus 1 positive 1 I'm saying. Minus 12, correct. Okay. If I use q as 1, it will be minus 12. Doesn't work. So I use q equal to minus 1. Quotient can be negative. Okay. Only the remainder that we want for it to be least positive residue, it is between 0 and m minus 1. The remainder is positive. Okay. So if I use q equal to minus 1, substitute in this equation. Okay, I'll just overwrite here. If I use q as minus 1, so minus 3 is equal to minus 9 plus, as someone had already replied, and it will be 6. Okay, do you get this now? Yes, okay. So the next concept that we have, this was modular exponentiation, and in tutorial I'll give you an example like this. What is the next thing? Okay, so okay, now we want to find the application of the extended Euclidean algorithm. I somehow have to finish this concept. Okay. Now ax. Okay, ax. Now what is ax? No, just consider. Okay. Instead of a is congruent to b mod m that we are writing, just consider that instead of that I'm writing ax is congruent to b mod m. X is also an integer. A is also an integer. Ax is congruent to b mod m. Okay. So now, by definition, I can say that ax minus b is a multiple of m. You can say is equal to km. Okay. Now, instead of k, okay, because I want to use the some other terminology. So instead of k is just a constant. K is just a not a constant. K is just an integer. Okay. So I can use any other alphabet in place of k. What if instead of k I use it is equal to y times m? Instead of k I'm using y. Okay. Y is just an integer. Okay. So now I take this ym to the LHS, and I can write it as ax minus my is equal to b. Ax minus my equal to b. Okay. Simple steps. Okay. Now I give you a definition. Okay, this part is clear. If any question you can ask. Okay, I think there are no questions. So I'll give you another definition. So we say that integers a and b are multiplicative inverses mod m if a multiplied by b is congruent to 1 mod m. Okay, so for example, 2 what so let's say my mod is 5. Okay, so I can say that 2 into 3, which is 6, is congruent to 1 mod 5. Therefore 2 and 3 are inverses mod 5. Or let's say 8 and 7, and my mod is 11. Okay, so 56 mod 11 is 1. So 8 and 7, 8 multiplied by 7 is congruent to 1 mod m. Therefore 8 and 7 are inverses of each other. Okay, now in general, let's say if we have one of the numbers, okay, if we have one of the numbers, let's say I only had 8 and I know that the mod is 11. How will I find the other number? How will I find its inverse? How will I find its inverse? Are you getting this point, whatever I'm doing? Are you getting my point? To find this inverse, one way is trial and error. Okay, you randomly try some integers, or you run a loop. Basically you go iteratively and you try with 8 into 1, 8 into 2, 8 into 3, 8 into 4, 8 into 5, 6, then 7, and finally you find that for you try every time. So 8 into 1 is 8 mod 7, 8 into 16 mod 7, 24 mod 7, 32 mod 7, 40 mod 7, 48 mod 7. Finally at 56 mod 7, oh sorry, mod is 11, I'm very sorry, mod is 11. Okay, so at 56 mod 11, you get the remainder as 1. And therefore, 7 is the inverse that we are looking for. But how do you find this number? What is the technique other than this, other than the brute force technique, other than actually going, through every possible multiple? Find the remainder for 8. Okay, now I have to ask you something. So it's almost 3 minutes for the lecture time to end as such. Are you ready to wait for 10-15 minutes extra and we can see the application using extended Euclidean algorithm, or shall we take it in next lecture itself? This problem we can solve using the extended Euclidean algorithm. So are you ready to wait for 10 more minutes and we'll see it now itself, or tomorrow? Next lecture? What about others? Next lecture, okay. I don't want to rush the example as well. So we'll see in the next lecture how we can solve this using extended Euclidean algorithm. Okay. So any questions, anything you want to ask? Okay, then I'll end the lecture here. Thank you.